for a little bit.
It was like crossing guards and
Kind of form and evaporate again, but
so it's mostly neighborhood stuff. So
it's not.
Wait for a couple
it's
more
not
minutes.
bad. He actually has to learn the bread.
Was that?
Yeah, I have to look at my notes too.
Yeah, I mean, it was not as energetic as some shows I've been to,
Yeah,
but like people were into it, people were singing along.
That's really cool. All those turned out.
Yeah, it was nice and
There's always that one guy who's like super drunk and almost gonna fall over the railing. Yeah, it was good.
no, it was
like there was more.
I know, it was like it was
audience than I expected. Like I thought the crowd was gonna like yeah, I saw a lot of people there who was like clearly.
Yeah, I mean, I think it helps.
Like, wow, Iron Maiden's still finding new fans, apparently. Yeah.
So like for a long time I never really had like
You kind of get into the mindset of,
Well, I mean, they packed that place.
Oh, yeah.
Sold out 15,000 seats. Like, okay.
I don't know which direction we're going.
I'm not even sure if it's out.
I can't build my mental map anymore.
I'm not. Yeah, I think there might.
Put that on.
Okay, it's my great pleasure to introduce June Andrunic. June is the leader of the Trustworthy Systems group at Data 61, so in charge of SL4 proofs and a whole bunch of other stuff. So June was here for ITP, and we're lucky enough to have her visit us. So she's going to do a modified version of the keynote for us, and will be available for questions for us today. So, thank you, Ray.
Yeah, thank you very much, Simon. It's my great pleasure to be here and see a lot of faces that used to be in Australia at some point as well. So yeah, great to be here. I was here for the ITP conference last week, and so this is the presentation, but I'm happy to adapt in a way that would make sense. Also, I hear people that didn't come to ITP and still wanted to hear about it, so I'll keep kind of the same theme, but happy to. I'm around for the day, so happy to talk about other areas that we're working on as well. So. As Simon said, I'm leading the Trustworthy System group in Australia. That's about 50, 60 people working on making software more trustworthy, like truly trustworthy software by the means of mathematical proofs. And about a month ago, we celebrated one of our key milestones. It was the 10-year anniversary of having announced the proof of the SEL4 microkernel, which is our small operating system kernel for which we had a formal proof of functional correctness. So that was 10 years ago. And a lot has happened in the last decade in the group. A lot has been beyond SEL4. So how do you build trustworthy systems or full trustworthy system on top of SEL4? How do we help with that? So there are a few areas in, for instance, making sure that you can make it more cost effective, generate a lot of the proofs for free. So we have projects using, for instance, KKML to do that, or using Cogent, which is our domain-specific language that can co-generate proof and code in a verified way. But what I decided to focus that talk on in the last decade is actually focus on the SEL4 proof itself and what happened to the proof itself of the kernel in the last 10 years. So what the title says is that it became quite large and it keeps moving. And that creates quite a bit of challenges that I want to talk about. And I try to focus the talk not so much about too specific to SEL4, but quite generic challenges that we had to deal with that. And there are quite a few people that have been in that group and that might know even more about some of the aspects, like Dan, who has actually already heard the talk. So feel free to talk to him as well. So to start with and put a little bit of context and motivation behind it, who that is, this is a mathematician, Pythagoras, from ancient Greece. And the second picture is about SEL4. So this is the call graph of our microkernel. So every dot is a function and every edge is a call. And that shows you the complexity of a microkernel. So I'll explain a bit more what a microkernel is and so on in a second. But just as a motivation, I wanted to say that a big difference that you might have between these two things, well, the thing that may be similar is that they both talk about a theorem. One of them is about a mathematical object, a right triangle. The other one is about a piece of software, the SCL4 microkernel. And I lied a little bit. There is no such a thing as the SCL4 theorem, because actually there are many versions of SCL4, especially in the last decade, and there's actually several degrees of properties that you can get about it. And this is what I mean by a moving target, is that probably compared to formal verification of big mathematical truth, when you are targeting formal verification to software, then you need to deal with a moving target. And so this is the outline of my talk. I'll first go a little bit more about what makes really the software verification a moving target, and why, in the second part, why do we actually really need to deal with that if we want to achieve that big dream of having more and more software being verified as a default. And then in the last two parts, I'll mention what are the challenges that this creates, and also some of the techniques that we have been developing in our group to be able to handle those challenges. So let's first look at, again, that moving target. So if I come back to that right triangle, I hope that we all remember by heart where the Pythagorean theorem is, but if you have a right triangle, then the square of the hypotenuse is equal to the sum of the squares of the other sides. And this has been around for a long time, but nowadays, when you have such a very nice object with a very nice properties, suddenly people want to build products out of it. And so just try to imagine yourself in this situation where people, you're in a kind of meeting room and you have your clients coming, your customers coming and saying, look, I really love your object, and I really love the properties that you have about it. But can I still have the guarantee if your triangle is not green but is red? You've put in that room as an expert, so people turn to you and say, is that possible? And you say, yes, of course. And that might remind you something that you've seen elsewhere. And so, as you say, of course, they get excited. And then they ask you, OK, does your guarantee hold if, for design purposes, your product and your triangle is, the right triangle is slightly bent? And so, as the expert, of course, you say, well, no, I have a right triangle. This is what the property applies to. OK, so that was kind of the entertaining introduction, but now comes the software. And this is SCL4. So now a small side intro to what SCL4 is. It's a kernel. It's a microkernel. So it's a minimized operating system core. So it runs at the core of any software stack between the hardware and the rest of your software stack. And it is critical because it's at the core of your software. And it is also its job to isolate software on top. So it is its job to isolate, say, critical application like the brakes in your car from the uncritical one like the entertainment system. So that's its job. And the key property, guarantee that we have, a unique feature is its formal proof. So we have a formal mathematical proof in a theorem prover, in the Isabelle Hall theorem prover, that we have functional correctness. So the code satisfies what the spec asks for, and it enforces isolation of the components. And so this is what created a lot of excitement. And as I said, excitement comes with people wanting to use that in products. And so this is where you might have customers that ask you, look, I really like what you're doing here, but I need to build it for other components that you have your example for. So would that work? And in this case, you say, yes, obviously, I have a for all quantification. I know it works for all components in my theorem, so I know it can work for any kind of components. But then they might ask, actually, I need to change the code slightly because I need to run it on this platform, or I need to have this kind of feature or this kind of extra system call. And this is where it starts to be a discussion and a negotiation. It's not, no, that's not my object. And the main difference is that you don't want your software to be obsolete because this is what they require. This is what they want for building their product. So that's the main difference between software verification and maybe verification of other things like mathematical objects, is that the target can change. And what I want to say here is actually it needs to change if you want to always be relevant, that you don't, that the main difference is that the software very quickly become obsolete. So if you want to make sure that you have impact, you need to be able to answer those requests from people that want to use it, which I'm sure you'll be very familiar with that kind of discussions as well. So what I call the dream is having verified software becoming more and more a de facto standard when it comes to critical software in particular. And for that, we really need to be able to have software that can be expanded, that can be evolving, that can be maintained longer term, which wasn't necessarily the case when we started 10 years ago thinking about that. And the way actually I phrase the challenges in the Trustworthy System group for the coming future is be able to prove that software verification, I don't know if it's the mic is, anyway, sorry about that. So it's making sure that software verification is cost effective, that there is no more excuses not to use it. And that's about, how do you generate proofs for free? How do you help making those tools much more usable and so on? The scalability of things so that you can actually target larger and larger software. And the last aspect is really what makes it a moving target, is how do you keep the software relevant to what people need? And this means that all of the, and that creates research challenges, as I'll come to in a second, but this is what makes it moving, evolving. So if I come back to the fact that there is no such a thing as one SCL4 proof, it used to be true, as I said, 10 years ago. So 10 years ago, there was one proof, and that was actually a breakthrough showing that you can do mathematical proof about real 10,000 line C code, low level, and real world software. At that time, what the proof was a proof of functional correctness. So this is in a formalized, so in the Isabelle Hall logic. So we have a formalized specification of what the kernel is supposed to do, a formalized implementation of it, and then the arrow is the formal proof of refinement, that every behavior of the C code is a correct behavior as specified in the abstract spec. And then, in the meantime, a lot of new versions of SCL4 came in, a lot of new degrees of guarantees, and this created, first, in terms of guarantees, we went down to the binary in terms of guarantees, so that the binary semantic is also preserved, and also further security properties on top, which ensures that isolation I was talking about. So it's proving that application, when they run on top of SCL4, SCL4 will enforce the integrity and confidentiality of the information that they manage. In terms of the different version of SCL4, this was triggered to the fact of being still relevant. So people were starting to ask for new platforms, so ARM, Intel, RISC-V, new features. So the two big items that have been coming up in the last 10 years, there's mixed criticality support and multi-core. So multi-core is quite obvious. The first proof was actually on a unicore platform, but people just said, look, we want now this to hold on multi-core platform. This creates big research challenges because suddenly you have to reason about concurrency. Mixed criticality is really a cool new feature about SCL4. So SCL4 treats, manages isolation by having a capability model. So basically, as you set up your system, you distribute access rights, which are capabilities, which gives you read or write access to pieces of memory. So this is a way to control the access to resources and the access to communication between components. And this is how you control the information, how the information flows in your system, and that describes the security of your system. Mixed criticality is about considering time as a resource. So having a capability to manage time, to prevent an application from overrunning and basically staying in its budget. And so this is a principal way to change the way the kernel runs, to be able to consider time as a capability and be able to have SCL4 enforce that the same way it enforce isolation of resources like memory. So these are two big new things that are happening on the implementation side. And just, I wanted to have one opportunity here to update on what has been happening on the impact or where that is used, is because we're able to listen to those requests, this is what creates the impact. Or the other way of seeing it, the more impact we have, the more requests we have. So that's kind of a circle as well. So in terms of the impact after that big first SCL4 proof, the main event that happened that created then the adoption by third parties was the HACMS program that was managed by John here. And this allowed to show that verified software could be embedded on real systems like these 4 autonomous systems, and also demonstrated that it was indeed preventing cyber attacks, or preventing, like, the system had critical and non-critical parts, and there was a red team that has access to the non-critical part, and we could show that it prevented them from reaching the critical part and getting control over the system. So a second big demonstrator that really showed that, you know, it could be embedded in real system is a project that we have with the Australian Defence. It's called a cross-desktop domain compositor, and this is the idea of having on the same screen being able to have multiple security domains in a secured way and in a usable way, rather than having multiple desktop on the same desk. And the third kind of big event, of course, is 5 years ago only, this SCL4 became open source, so people could really play with it and try it. And altogether, this really led to much more of third-party use. Oh, and the transfer to this laptop seems to have gone the layout a bit. And it's through all this, and some of these projects are together with us, but they're also sometime on their own. So there have been a lot of people that just adopt the SCL4, try it, and so on. And this is through this impact, through this application, that people start to have new requests, and that then suddenly not only requires us to evolve the implementation, but think about what it means for the proofs. And so just to summarize, what I want to take away here is that we really need to be able to manage that if you want to have that kind of impact, and we want to push that dream of having verified software as a default. But of course, this is not easy. So now I'm going to talk about the challenges that this creates in terms of dealing with that large artifact that keeps moving. The way I try to phrase it sometimes is that we have 2 challenges, the matrix challenge and the month-year challenge. And I'll explain a bit, and then I'll come back to why I call them this way. But if we come back to the several versions and several levels of proof, these are the different configuration ticks that you can take when you decide to use SCL4. SCL4 exists on 3 types of platforms, so ARM, Intel, and RISC-V, in 2 kind of modes, 32-bit and 64-bit. And then you either have the single core or the multi-core version of it, and that's all in the implementation side of things. And then either you have the mixed criticality system, which is, I say, it's a new feature of SCL4, or you don't have it, which is what we call vanilla. So it's basically the previous version. And this is where you start to see the matrix, which is actually a 4-dimensional matrix, which has all the different ticks that you can take, and that creates a lot of configuration that you have to handle. In terms of the levels of proofs that we actually have these 3 levels that I'll summarize into the functional correctness, the binary verification, and the security proofs on top. And depending on which configuration you pick, you would have a certain level of guarantees. And actually, this is the version that we had 10 years ago. So 10 years ago, it was about the first line. So we started on the ARM platform, 32-bit, single core, and vanilla. So that's the first line of each of that matrix. And we had that full stack. Actually, in 2009 was just a functional correctness, and then it was about in 2013 that we had both the binary verification and the security on top. And in terms of sizes, we keep saying that the C code is about 10,000 lines. It might be 15 now, I'm not sure, with all the new features. And the implementation, about 10,000 lines, correspond for one stack about 500,000 lines of models and proof in Isabelle. And then there's the rest. So as the implementation evolved,
Quick question about that.
Yeah.
100,000 lines. How much of that is just reusable libraries in Isabelle that you could imagine? Like, I've sorted those libraries out, I just get to use them.
that's my understanding is that this is just for that stack. So we separate it from all the libraries. But I could go into a bit more. I'll check again exactly what that is. That's correct. That's a good question, I mean. And then we have basically 3 platform ports. One was for Intel. It was actually part of the HACM's program as well. We went directly for 64-bit here, but we stayed on single-core vanilla for all of the platform ports so far. We had also a port to the extension, the hypervisor extension of ARM, and we're working on a RISC-V big project right now, a port of the proofs for RISC-V. All of this means that the implementation exists, and actually the implementation exists for most of those configurations, but the proof only exists, and partly only for some of these configuration. And now we're also working on the 2 big new features of SCL4, which is the mixed criticality support and multi-core. And for both of them, we basically, for now, until we have full stacks on the others, are basing it on the one where we have the only full stack. And all of this is driven by contracts or by demand, and that's why it creates that multiplication of stacks. The other thing is, during all of that, we have a kernel team that keeps wanting to do some small changes, implementation, optimizations, and so on. So as we do that, we need to be able to incrementally integrate all of these changes as well. And this is what creates the million lines of a moving target. A bit quickly, if people are more on the formal verification side, I wanted to mention a bit what different types of work it involves from the formal verification side. And when it's a different hardware, because it's a microkernel, a lot of what you might think is very low level is still visible at the specification level because it's needed for the applications to know about it. So one example, for instance, is the way the hardware will lay out its memory in terms of pages and page tables. So how do you access those pages? And these different hardware will have different number of levels, so two-level page table or 3 levels page table. Some of them have the same kind of page table, some of them have different from different levels and so on. And so these are the kind of things that need to be updated up to the spec level, and also you need to reprove some of the invariants. So a lot of the proof for the functional correctness involves actually proving a number of invariants about the abstract spec before even starting. In terms of the mixed criticality, this is one of the biggest change we have about the kernel itself. We're actually adding new system calls to deal with these new capability. So we need to think about new invariants and how much it breaks the previous invariant. So that's one of the major changes that we had. The multi-core is at an early stage because it actually changes the whole model of thinking about it. The refinement will not be the same kind of refinement and so on. So this is just adding the whole idea of concurrency behind it. So we've worked mostly on the framework itself, and we're looking now at adapting the formal specification. And so coming back to the way I phrase it between the matrix and the month-year challenge, the matrix challenge is that you have all this kind of configuration that I managed to just put in a 2-dimensional, but as I said, it's more like a 4-dimensional. And for each of these cells, you have, do we have the code, and to which level we have the code, and do we have a proof, and to which level we have a proof. And so this creates just a scalability issue, like how do we make these new cells in a way that is manageable. The second problem is that when we have people coming to us and talking about a new feature, a new port, implementing it is in the order of months, proving it is in the order of years. So just to give a bulk figure. And so that creates that gap. And this is what I represent like this, where you have the implementation that keeps evolving and keeps wanting to do new things, and then turn around to the proof side that keeps growing bigger, but also is always slower. And so we need to have a way to better manage that as well without stopping the implementation from evolving. And so now I'll go into some of the approaches. There's no clear answer of, yes, we know how to do that. It's more like sharing a little bit of the things that we have been implementing. This is a little bit oriented towards theorem proving. As I said, it was more in the context of the Interactive Theorem Proving Conference, sharing a little bit of that, and also trying to get some of the community to share as well in terms of their projects and their approaches. I'm keen to hear if there is any insight from this room as well. So this is the Trustworthy System group. So we have people both from operating system discipline, formal method discipline that are working together. And it's also a combination of research and engineering. And within that group, we have the proof engineering team, which is about 10 people currently. And these people are the guardians of that million lines of proof. And these are the people that are creating those stacks and have to deliver on specific projects about proofs. And a lot of the things that I'm going to say in terms of the challenges and the approaches is because proof engineering is a fairly new discipline, and therefore some of the stuff is we're experiencing as we go. And some of the challenges are quite similar to what you would see in software engineering in the early days, but we have much less experience and big projects like ours to share, best practices and so on. But one of the most common similarity between the two engineering fields is that you keep having to always make a choice between two things when you have an engineering project. And I'm pretty sure you would have experienced the same. So what would you say when you have to do an engineering project would be the two things you keep balancing? Anyone? It's between now and perfect, right? And when you have a deadline, anything with deadlines is between doing it now because I need to deliver it and I have a deadline, I need to do it, and actually, I want to do it perfectly and I want to do it in a very generic way and it's going to be awesome for all of the further project, but I'm never going to deliver. So this is also true in a lot of things that we're saying. That's why there's no clear answer, but more like a balance things that we've been trying to understand more of as we do those projects. And this is also why, at the moment, we have quite a bit of this duplication of stacks, but we're trying to make it in a bit of a better way now to handle further projects. So it's a bit of that balance. Okay, so the way I approach this is that we sat down with the proof engineers and we discussed what are the things that we might be doing differently because we have these very large proof artifacts or because we know that we're going to have to maintain it for a very long time. So I took a lot of notes. I identified common themes. I came up with names that would, represent those themes, and with the first letter, I just extracted the first letter so that I tried to remember it. And this is what I came up with, about 7 kind of themes that came up. Some of them that looks like ASAP, and that are actually around how do you make sure that you can follow up the pace and so on, but I'll come back to that. And 3 themes that are more like, it came up with MRI, but it's about how you actually look into the proofs when something is going wrong and so on. So this is just one way to maybe remember them. So I sometimes ask, would people guess some of them? So what would be your main thing if you had to do verification of something over and over, or that if you need to, yes? Automation, yes, one of the A's. The other A should be, is also so often found. Abstraction, awesome. 2 brownie points here. All right, I'll put them here. So, and some of them was just to find a name that makes sense, but you have automation. I'll come back to what I mean by standards. You have abstraction. The parallelizability or modularity is in terms of people. How do you parallelize the work between a big team? And then M is about maintainability. Refactoring for the R. Introspection is how to look inside the proofs or inside the theorem prover to know what's going wrong. So what I did is that I'll go into examples for each of them. Again, I can go a bit fast on that because they're quite a bit theorems prover specific. But it's just to give you an idea of the kind of stuff, and I'd be interested if there's some similarities in some of the things that you might be experiencing. So in terms of automation, is when you have to deal with million lines of proof, you need to, as much as possible, save your brain where it's really needed. One of the examples we have is we have developed some tools, we have much more, but one of them is to be able to crunch through proof automatically. So a lot of our proofs are invariant-based proofs, so you want to prove that a function f, if it starts in a state that preserves an invariant, it finishes in the state that preserves the invariant. And we have 500 functions for that. And the invariants are broken down in pieces, and therefore we have many small statements about small invariants that we want to crunch through. And what we do is basically automatically traverse. So we apply crunch as a proof technique, and this automatically tries to prove it for all of the function calls recursively. And if it manages to prove all of them automatically, then you're done. So it's basically about automating a lot of the proofs that don't need a lot of brain, so don't need a lot of interesting facts. And so one aspect that I was saying is when you deal with million lines of proof, you really need to use that kind of automation because otherwise there's too much to handle. And when you talk about interactive theorem proving, you need to be able to interact in a way that the theorem prover does everything that can be automatable and you only call in when it's really needed and not spend your time. When you think it's too easy for you, then you should try to find a way to automate that. But that's when the balance between now and spend your time automating. And why is it so specific to maybe software verification is that in our experience, so the software verification is dominated by these invariant proofs. And a lot of them are not that interesting. Some of them are, when you set them up, thinking about the invariants and so on is really where the involved process is. Actually, proving some of the small one is not that interesting. And the proof itself is not that interesting to reread it. And so that's where automating it is really important. The second one was more about kind of standard of engineering and the importance of doing code reviews, proof reviews in here, and a testing infrastructure as well. So we have a whole regression testing infrastructure. But also what I found interesting here is to be able to have that collaboration between the proof engineering team and the kernel engineering team in a way that they can keep exploring on the kernel side if it doesn't impact the proof. So we have a testing infrastructure that when the systems engineer are working on the C code, so as I said, the C code would actually, you have one C code and through configuration that gives you all of the different variants. And so they might be working on some changes that might change only one variant of it. And they might want to know if that would impact the proof. And there are cases where it doesn't, right? So you might have multiple cases. You could be touching a configuration that is not at all verified. You could be touching a verified configuration, but in a way that the proof still holds because it's robust enough, and I'll come back to that. And if that's the case, you want to be able to basically integrate it automatically. Now, if you're actually doing a code change that breaks the proof, it shouldn't be integrated, and you should actually stop and talk to the proof engineers to be able to have a side project to integrate it. And that's how we have patches that are delegated to the proof engineering team to be able to prove them, and then the C change can be integrated. And have that supported by an infrastructure is really important. So basically, you need to allow exploration on the implementation side. And that's that example. I don't have specific examples, but proof review turned out to be really important for several reasons. One is maintainability. I'll come back to that, but it takes experience to know whether a proof is going to be easy or not to maintain longer term. And it's also good to have proof reviews to get the newcomers in the team to learn that, as you can provide feedback through that. And then the last one is actually identifying abstractions. If you're reviewing a proof from someone else that is very similar to something that you're doing, but you're never going to look at their proof because they're in a kind of parallel thing, by doing proof reviews, you might identify things that should actually be abstracted in something that would be higher level. Again, quite similar to something you might see in software engineering, but applied to proofs.
So June,
Yes?
how long does this process take for running the proofs to see whether something's broken or not?
So, this one?
Yeah.
That's a good question. I'm not entirely sure. So I think all of the proof structure right now would be about like if you run it entirely, about 2 hours. So it's not something that, yeah. So we have the nightly build that, I think it went between 2 and 5 hours, for the nightly build, and yeah. So that's in this order. So it's not something that you would do, every half an hour to check something, but that's something that you can do before integrating something and before having to meet with the proof engineer, or know if you have to meet with the proof engineers and so on. Yeah. Okay. Okay, so leading to the second big A, so automation, and the second one is abstraction. Abstraction is really important when we have to deal with different versions of the software, in particular when we have platform ports. And this is something that we didn't have that to start with, and this is the bit of the balance. So we are now looking into doing that more and more, but it's an ongoing process because we have legacy of what has been done so far. But basically, as I said, some of the hardware features need to be represented at the spec level, but right now it means that we have 3 different spec. But obviously in the ideal world, you have everything that is architecture independent, separated one with what is architecture dependent, and this is what can change, and then you have a nice, neat interface between the two, and then if the interface is done nicely, then the proof shouldn't be impacted if they only change the proof, the architecture dependent stuff. So we're starting to do that in particular for the RISC-V platform, which is the newest one, and we're trying to integrate more and more of that. So we're using parametric features of the Isabelle theorem prover, like locales, to be able to do that. And in a way to have the interface. But as I said, it's an ongoing process. This is not what we have right now. We're trying to have it for RISC-V, and we're trying to have a bit more of that split also. So we already start to have that split at the, so that Arch split is basically splitting what is independent. So it's an ongoing process. One thing compared to software engineering is refactoring in some way is safer than software engineering because you know if the proofs are broken or not. But it is also more costly if you do it too late. So that's a bit of a trade-off that needs to be thought of. So it's good to take some time to think about those interfaces. Of course, you will only know how useful they are and how efficient they are once you've reached the state where you have multiple instances. And this is just one example of abstraction. We have much more example of abstraction in lemmas and in the architecture, and there's more room for that. And the last in this ASAP kind of family is how do you parallelize the work between people? So that's more about people. And that's the idea that's more like heuristics. The idea is that you want to be able to quickly have either manually or automatically ways that when you're proving a specific lemma, that you can invoke some kind of automated way that would dispatch it to multiple people. So you create specific small lemmas, you sorry them, which means that you assume them, and then you dispatch them to people so they can prove it in parallel. So for instance, some of the automated techniques or method that we have developed, like the CoRES here that I mentioned, which is a way to decompose your function in its structure when you do the functional correctness proof, allows that quick decomposition between different people. And you can push that further. So that's just the idea that when you have large artifact like proof verification, you need to have large teams, and there's no, as I said, clear way of doing that in the proof as opposed to code, but it's a bit the idea of decomposing that. And then now the three themes are around MRI. So M is maintainability. The interesting thing is that when I started informal verification, what I found it beautiful is that if you're not doing math proof that someone will reread, when you've done QED, you're done. Like, there's no reason why you should, a nicer proof, because, it's done. But now, if you're going to have actually maintain it for a very long time, that's someone else. That if it may be broken because you're going to update the software, then someone else might have to fix that. So there needs to be some kind of rules about what makes a proof more maintainable. And there are two main aspects here, which are actually the two obvious things when you do automation, which is automation is usually great because, you do less things until it doesn't work. And so until it doesn't work means that when it doesn't work, then it's more painful usually to know why than if you had done step by step. And so one of the things, the experience that we try to build is what makes a proof change resistant. So if you have a proof about a specific software piece and your software changes, well, you have several cases. One, your statement is not true anymore. And then you have to think quite a bit about it. So there's nothing you can do about that. The second thing is your statement might be true, and then either your proof still works, which is what you want, or your proof breaks. So you want more and more proofs that still manage to hold, even if you have small changes in your software. And for this, there are a few heuristic or experience that we've built. And then, of course, the more you do that, you still need to be easy to check if actually the proof breaks. So I might go quickly through that, but the idea is that when you do proofs of code that may evolve, you might want to do things that are a bit more generic. So this is an Isabelle way of invoking a simplifier on a certain rule. So rather than having a rule R1 that you apply to simplify your goal, you actually have a set of rules, knowing that more of that set will apply to more of different kind of statements. Meaning that if your statement changed a little bit, your proof would still hold because they're going to pick in one of the rules that would apply to that goal. And the other thing is, a lot of the automation can leave a mess. So in particular, you might have automated method that create, so these are the numbers of sub-goals that are left in Isabelle. So you might invoke an automated method that leaves a lot of sub-goals, and you don't know which one you're actually now proving. And if something changes in your statement, you might end up with a mess that you don't know where it has actually broke. So the general rule here is when you use automation, you need to leave a clean state, meaning that you have to solve an entire goal so that if it breaks, you know that this is the line where it broke, and you don't have 10 lines where you don't really know exactly where it started to break. Yes?
Maybe this is too detailed, but
Yeah.
so with this thing you have at the top, when you have R1 and R2, you sort of only have a dependency on R1 and R2.
Yep.
On the bottom line, you have this sim set now, RS.
Yes.
So now whenever I change RS, that's going to impact everything which uses RS, rather than if I change R1 or R2, which only impacts the place where it's used. So do you have any thoughts about how easy it is to kind of add things to RS and not break proofs?
So I'm not sure. So it is true that the more you use, so actually that's one of the rules that that we've been discussing, that it's better to actually have a specific set of rules rather than actually adding to the general Isabelle sim set, because that's exactly the thing, is that if you change it a little bit, then you don't know if that's why the sim set didn't work anymore. In that specific example, yes, it's true that you'd have maybe more proof if you do change R1, but if they break, it then means that it was relying on R1, so you'd have to fix it.
But if you add, that's all right. We'll talk about it.
Okay, we can talk about it, but it might come to the how do we check why a proof is broken in the last item. Yeah.
Do you have anything for kind of checking if these policies are being followed, or is it just kind of word of mouth? You remember all the policies?
Oh, that's a good question. I think it's not as documented as we would want. So there is a little bit of, and that's where the proof reviews can help. But it's not as I said, this was actually the biggest exercise that we had through that. But you might have a different view. Yeah.
At some point, we had the indentation script that checked that
Yeah.
all the code, it was all indented based on how many cycles were open.
So I think we have many things that exist, and that I don't think we have a specific guide of saying, look, if you join that proof engineering team, these are all the things you need to follow. Although when I joined, there was this beer offense about if you actually use an automated method, which doesn't solve completely the goal, and you have something afterwards, and it's a pain to update. So if someone else is updating a proof where you have done that, you owe them a beer. But that was kind of unknown things. Then there is more automated ways of making the proofs more automatable.
Yeah, so there's a lot of infrastructure you can build that can check a lot of these things. But again, things closer to the top, that's more the sort of,
Yeah.
you kind of just feel your way through.
So I think we have both a lot of, and these are, as I said, just very small examples I've picked out, but we have a lot of automated ways of doing all of that. What I said might not be as documented is a list of all these things that people should kind of follow. Although, it's quite, we have quite clear of guidelines in terms of how a proof should look like and stuff like that. But this keeps being discussed as well. Yeah. Does it answer your question? Yeah. And actually, this whole work was to start having a little bit of that as well, to start listing a bit of that and make sure we can also share it externally to gather feedback as well from other groups. The refactoring is also always important. We have like very large proofs to avoid, as in software, duplication, unused parts, but also move lemmas. And this is quite important because the way a proof works, this is a theory graph. So what that means is that at the top here, let's say you have the root at the top, and this is where you have the lemmas that are imported by everyone. So that's an import graph. And so what it means is that when you're in a specific theory, a specific file, so this is a file where you're actually proving right now, all the lemmas that are accessible to you are your parents. And what that means is that when you have a structure like that, it's very hard to know if there's not someone else in your neighbors that are proving something that is very similar, right? And so a lot of refactoring, automated refactoring, is really important, either to remove duplication, because duplication will happen if people can't see this, or actually to levitate lemma a bit higher up so that they can be seen by other people if they're not part of your proof. But what happened on the day-to-day is that you're about to prove, you think your lemma might be interesting for other people, but you want to move it up to the actual library where it belongs, because that's going to take you 2 hours to rebuild the image and be back to your point, so you might tag it as moving me later and so on. So refactoring is a necessity. It needs to be automated and in conjunction with a testing infrastructure that would apply it automatically if nothing breaks, because it's quite fragile. We were talking about simplifiers and what is in the sim set and so on that can break things. And one of the things that I mentioned was that this is quite fragile with new versions of the theorem prover, unfortunately. And that's why actually our levitate lemma has been not updated for a while, because it's a bit of a pain. So this is kind of a discussion we need to have with the interacting theorem proving community to be able to have that a bit more stable. And the last thing, which is how to look into the proofs when something actually breaks. And this is also, like if you apply automated methods, so I said, oh, we should do more and more automation, but then the automation, so you might have built a method that, proves many goals. But one way of using it is to know when it breaks, what to do. And so an apply trace tells you what rules have been used. You can click on them. You can realize that one of the rules used to be applied and is not applied anymore. So you basically run the previous version of your proof with a new version of your proof, and you can actually check, you debug basically your proof. And so there's a lot of tooling around that, mainly based on the language ISPAR that Dan developed for building methods in Isabelle. So this is really, we have a moving target. We need to understand what have changed. So we need to have tooling around debugging those proofs. So this is the summary of how I tried to gather all these thoughts from the team. I had also asked them, is there a wish list of things you want to see more of? There was the idea that there is still some scalability or performance issue on the theorem proving side, that some of the specific techniques that we use, like locale, that allows parametricity, are actually have performance problem when it comes to very large proofs. Slower, that's more like in parentheses, that's more for me in terms of making sure the project can come in a slower pace so that we can actually do a lot of that refactoring so that we're not too much on the now balance. There is more abstraction and automation that we can work on internally, but it's also some of the things that I mentioned in terms of making sure with the theorem proving community we can have more tools for this kind of refactoring, introspection, sharing more of those tools with the communities. And having people that are smart and want to come to Australia doing proof engineering. And this is the last bits of wisdom that comes from our Yoda, which is go incline. So that's just to finish on a few food for thoughts. Making it cheaper costs money, and this is with that balance, saying you need to have to allocate time, resources, and so on to make it cheaper for the longer term, but that costs money at some point, so that's one thing. The second thing is the way we've done, the way that proof evolved was because we haven't planned to start with that it's going to be a 10, 20-year maintenance and that the proof will have to be updated in that way. And that's why right now refactoring is a bit painful because it has been to be done while the other projects are going. And the really last remark is that, as I said at the very beginning of this talk, it's really a trade-off. So that's why there's no clear solution, that it's always a trade-off, but that we need to manage better in a way that we know when we have a bit of bandwidth to be able to automate something. And that's about it. So I think as a takeaway, the goal really of the Trustworthy System Group, and hopefully with a lot of the community that we share here, is to achieve a world where we can really trust the software that is embedded and deployed. And for this, we need to be able to manage that verified artifact that can keep moving and continue to develop those proof engineering tools to manage that. I'm happy to talk about any other areas that Trustworthy System is working on. I'm here for the day, but otherwise, thank you very much and happy to take questions.
So I was wondering, your kernel team, to what extent are they thinking about invariants and assertions, or is that something that the verification team just has to figure out separately?
It's a bit of both. So I think as we evolved in that team, so the two teams work very closely together. In particular, when code changes have to happen, there's a lot of consultation. That said, it's probably not early enough. So it's true that a lot of the changes would happen, and then it's when we start looking at verifying it. It's again a trade-off. Before they know it's going to actually be designed in this way, should we start looking at the invariants? But that said, it's more when the verification starts that we start thinking about what properties make sense, which invariants are true, and so on. And in particular, when they're not true, go and check with them why, and was there any reasons why it wasn't done this way? Yeah. Yes.
Sort of related. When you start the proof process, then do the proof engineers ever get to go back to the software engineers and say, it's been written this way, and this is completely impossible. We can't do it. Like, what is the back and forth between the teams like?
Yeah, so this happens a lot, and that's why I say we're very integrated. So this happens a lot. I think, even during the initial phase, it was very much a question of discussing there was a lot of things that would make the verification easier. And so we would go to them and say, look, we did have a performance impact if we actually would do these things in this way. for everything that is major changes, this involves a discussion even before we start, discussing, okay, this is the design, usually involving Yoda, and asking, look, this is the change, this is the design we're thinking about, and is there any chance this is going to, make sense from a verification point of view? Is that going to be a nightmare and so on? So this is going both on the high-level design phase, and then on the day-to-day, I'm proving that specific part, how much can I change it so that it makes it easier? And that's why it's quite iterative. Right now on the MCS, the mixed criticality, this happens a lot. And a lot of bugs have been found in this one, like everything that is not verified, we keep finding bugs. And so we need to also keep going back and forth and checking, what is the best way to fix it as well when we happen to see that. Sorry, yeah.
My question was also related to that. I was wondering, have you found bugs? So usually there's bugs in the software, but oftentimes there's bugs in the specification.
Yep.
And it's kind of who decides that you prove the right thing. Kind of there's some very high level.
Yes.
So how does that work?
So yeah, we found bugs in multiple levels, and then there's the obvious thing, is a bug at the spec a feature, and how do you know that then, So when we did the first proof, that was often the question. You've just proved that your code is as good or as bad as your specification. So any of the further proof that you do on top, like the integrity and confidentiality proof, are ways to basically test or put more guarantees about your specification. But that's always the gap in formal verification. But same thing that testing. How do you know that your test cases are actually the ones that shows that the software is correct? So there is that gap. So doing more proofs about your spec is the natural way of getting more confident about your spec. But there were cases where there were some discussion about, am I doing that? I'm not sure. Anyway, there were cases where there were discussion on the fact that the specification was written in a way that was more misleading the potential user, but that was still the intended use. So that was more like the borderline cases where we had discussion on that. But otherwise, just to make sure that the spec is correct, it's about doing further verification.
And related to that, who reads the spec? Is it mostly the proof team, or does the kernel team sometimes look at the spec?
Oh.
So presumably the spec is the most important.
Sure. Yeah, no, that's a good question. I think recently there were quite a few people involved in the systems team that were looking more specifically at the invariants. Okay. But to be honest, I don't think it's, the main people reading it would be the proof engineers as well, yeah. Yes?
So I was curious to what extent when you have one of these big formal, especially the functional correctness proofs, to what extent you end up having what I would call sort of theories or limits of pure mathematics, where it's just sort of things that don't depend on the code at all, that then just get used during formal verification versus like you import the code right at the top and do all your verification sort of within the scope, if that makes sense. I was just sort of wondering what the breakdown is of how much is support libraries, how much is stuff that's specific to the code.
I would say, so a lot is related to the code. Then there might be more generic stuff like word proofs and stuff like that. I mean, we have some libraries. So originally, when we had the first project, we separated a lot of what was generic, but that was something like the framework. How do you verify C code? How do you have the refinements? All of this is kind of done, let's say, once, right? And then everything that is, say, the functional correctness proof are two kinds. So you have invariant proofs about a given spec, and then it's about, this function refines that function. So all of them is basically, all of the statement looks like that. The libraries are very, as I said, word proof, specific to maybe data structures and things like that. And we might add more and more to those libraries. But I would say that, the biggest part of the generic stuff was the infrastructure of the proof, Sorry. Or you want to add to that, or yeah?
So I've been using a system called Ivy, where the idea is to develop verified systems by breaking them down into modules, where each module can be dealt with a a well-defined theory,
Yep.
preferably decidable. And this makes proofs very robust because now if you change it, it's still decidable as long as it's still right, the proof will go through.
Yep.
And it's also nice for interactivity and so on. And I was wondering if you ever have considered such an approach.
So this is a quite, I mean, putting things into module with nice interfaces and so on is kind of a natural approach. I mean, doing it with actually decidable theory behind it is great. The main thing is this is the kind of approach we're trying to investigate at the user level. For the kernel itself, often the way you structure your software will have impact on the performance. So if you try to build that same piece of software but with very separated modules with nice interfaces, and some other people have done that, then you have a performance impact of going to those interfaces. I don't know if the question was about the software itself or the proof itself.
Well, I guess it's both,
Yeah.
because there's a relationship, like you can.
Yeah,
you can make
sorry.
modular and the software is not modular, I guess.
Not really.
You can, but yeah, go.
You can to some extent, but essentially the proof follows the structure of the code very closely, and the code is highly non-modular. it's very sort of tightly coupled. Therefore, it's not. There's really no way to look. Oh, okay. Well, there's a nice model that I can build that's independent of the rest of the proof. The whole thing kind of ties together else, and this is reflected in the concept of proof.
But maybe you could take some pieces of code and kind of abstract some of the details.
So
Just the abstraction to the rest.
I mean, this is what you do when you do invariant cell reasoning. You come up with, well, what is the orderable bit character that we classifies this state for this function, and use that as the.
So I think there is 2 points. In one of the aspect is the idea of a microkernel is everything that can be modularized and put, like separated, is not part of the microkernel, and you put it in user lane. So that's also why it creates that very entangled structure. There is more.
Data structures, let's say you have
Sorry?
Maybe you have data structures that you can compartmentalize.
Yeah, so we try to do that. So even the arch split that we're trying to do is there is room for a bit more modularity in the proof side as long as it doesn't impact, like forces a structure on the implementation side. Yeah. Yeah.
Maybe take that offline. It's 12 o'clock, so I'd like to thank the speaker again.
Okay,
and,
thank you.
Jill will be around for the rest of the day, so come see me if you want to speak to her, or she'll be, I think, in this room here.
Okay.
So if there's nobody else there.